All right, kiddos. Now that we've got our graph and some key terms labeled, let's see what we can learn from it and if we can discover any trends in our trend. All right. So if you were to write down the equation for the line of best fit here, you would have gotten the kinetic energy, which is on the y-axis, equals something close to 6.6 times 10 to the negative 34. Okay. And so, and that is in joules per hertz, right? But a hertz is 1 over a second. And so this would be joule seconds. Interesting. Now, those of the graphs that I saw submitted, I saw a couple graphs. One had some calculation issues regarding converting from joules to kinetic energy. And another graph had the axes flipped. So at least the graphs that I saw didn't have this exact number for the slope. Okay. And then if you were graphing, you actually do need to graph the full values for kinetic energy and frequency so that you can get a slope that's times 10 to the negative 34. And then this is times frequency, right? It's our linear relationship. And we've got a y-intercept that is negative, and it is our work function. Okay, so that's the line of best fit. And what you would have noticed is if we were able to all compare our graphs, which is what we would have typically done in the classroom. Some of you would have graphed sodium, some of you would have graphed potassium, and you would have found that everyone had the same shape graph. It would have been proportional with a negative y-intercept. The slope would have been the same for all of your graphs, but the work function would be different, right? That y-intercept would be different. I think I've got some of those graphs up here. Yeah. So our two different surfaces, our two different target materials, they would have had the same slope. They'd be parallel, but they would have different y-intercepts. Just because it takes different amounts of energy to unbind electrons from different elements. Okay. So my question here is, what is this? This number should look familiar. And we can use this to write a generic equation. So we can say kinetic energy. And this is the kinetic energy of the emitted electron. Excuse me. And that is equal to 6.67 times 10 to the minus 34. That is Planck's constant, lowercase h, times F. Hey, we saw energy equals HF up here. What do you know? Okay, so that tells us that part of this relationship is the energy of the photon so the kinetic energy of the electron that's emitted from the photosurface depends proportionally on the energy of the electron, or energy of the photon that collides with it, minus that work function, right? And that work function depends on the properties of the material itself. So this is the work function. Right, and it's the work needed to bring the electron to the surface, okay, of the material and ready to actually like do some moving. Okay. Now, we also said that like the one of the patterns that we noticed was that the electron won't always be moving off of the photo surface, right? We don't always have current. There's a specific frequency at which electrons, specific frequencies, the electrons are emitted from the photo surface, and there's a critical frequency at which this starts to happen. So for the critical frequency, right, if we take a look at our relationship, EK equals Planck's constant times the critical frequency minus the work function, right? At the critical frequency, an electron has just been emitted from the photosurface, but it won't have any kinetic energy. It has just been liberated, but it doesn't have any energy to move. So at the critical frequency, the kinetic energy is 0. And any frequency below the critical frequency, there won't be any kinetic energy. So for the critical frequency, the energy of the photon, right, HF, is equal to the work function. We've done just enough work to get the electron up to the photo surface, but not have any kinetic energy. So that's an important equation, specifically for the critical frequency. And then this guy here is our photoelectric effect equation that we can use. Okay? All right, so here are some of the take-homes. You've got a photon incident on a metal that has a specific work function. If the photon's energy is less than that work function, the electron can't be liberated from that material, and so no electrons are emitted. Okay, so the electron stays into that material. It doesn't have enough energy to get out. If the energy of the photon is exactly equal to the work function, right, the electron is able to come out of the material up to the surface, but it will just stay there. And then finally, if the photon has enough energy, the photon energy is larger than the work function, the electron comes out of the surface of the metal material, and it's got enough extra energy to have some kinetic energy and actually come off of the surface with some kinetic energy. Okay. I kind of like this analogy, but it's a little bit goofy for some people. Okay. So a way that we can think about electrons being emitted from a material through the photoelectric effect, we can think about it in the same way as like if someone were standing in a pit, right, down at the bottom of a hill or something, and trying to kick a ball out of that pit. So we can pretend that the photons are like the kicker. They're the things that are giving the energy to the electrons. And the ball is like the electron. It is the thing that is down in the pit that is gaining the energy from the photons. Okay, so the kicker is the photon giving the energy. The electron is the thing that's down in the pit. And in this analogy, it's the ball, and it's gaining the energy from the kicker. So one of the things we can say is, depending on the depth of the pit, there will be more energy that's required to get the ball out of the pit, right? Just thinking about the law of conservation of energy. If the kick isn't hard enough, if the ball doesn't have enough energy to get out, it will fall back down in, right? If the kicker kicks with enough energy that is just enough to get the ball to land on the top of the pit up here, right, it will just land, but it won't have any kinetic energy, right? But if the kicker kicks with enough energy to get the ball out of the pit, and the ball still has enough energy to go beyond the edge of the pit, right, then this extra energy will be kinetic energy, right? So the kinetic energy of the ball, right, this kinetic energy that the ball has when it's come out of the pit, is equal to the kick's energy, right? The energy, the kinetic energy that it had down here from the kick. And it was, as it was gaining gravitational potential energy, losing kinetic energy, right, to get out of the pit. And then, so the kinetic energy the ball has when it reaches the pit surface is equal to the energy that the kicker gave it, minus this mgh, right? Minus the gravitational potential energy that had to be overcome to get out of the pit itself. So that's kind of an analogy for the electrons, where oftentimes we actually call the work function, right, the amount of energy required to get an electron unbound from the target material surface itself, we call that a potential well. Okay, and the deeper the potential well, the larger the work function is for that electron, and the more energy is required to get the electron off of the surface of the material itself. All right, I've got a couple examples that I'll post in the next video. Sorry, this is kind of a long lesson. Your homework that I'd like you to do is, I want you to take a look in the Oxford text at the photoelectric effect and the photovoltaic cells. And then there are some problems that I've attached about the photon and the photoelectric effect. In the next video, I'll do the examples that will help you solve those problems.